But it won't work because we know gravity is physics. And that's the physics we're doing today. So if we're talking about gravity, we are talking about Kepler. So we got to talk about his three laws. You got to know his laws mostly for historical things, but we do, there might be one problem on your quest about Kepler's laws. The first one says that planets don't go in circles. Planets go in ellipses. And essentially, that is true. Now when we draw them, sometimes we draw them like this one up here where they're really elliptical. Really, planets are almost circular, just not quite. And that helped to explain a little bit about why some of the astronomical calculations they made weren't quite right. And Newton used that fact to show that the force of gravity is proportional to the inverse of the square. So that r squared on the bottom, he proved that part using the elliptical orbits of Kepler. In fact, Newton had a lot to do with using Kepler's things to explain things. He also used his second law, which said that equal areas are traversed in equal times. So like if I'm really far out here and this is my area out here, that's the same area as the area when I'm close. If I made the area of those little pie-shaped things, they'd be the same areas. Thus, if you're close, you have to go really, really fast to get the same area, because when you're really, really far away, you have a long side to your triangle, and to get the equal area, you go a slower speed when you're farther away. And he used that to prove that angular momentums were conserved. And the last law, the third law, says that the period, the amount of time it takes to go all the way around in an orbit, is proportional to r cubed. And so this is the actual equation. But a lot of times we say that since t squared is proportional to r cubed. We can say that t of the Earth squared over radius of the Earth squared is equal to the t squared of any other planet over the radius of that planet squared. So I can find the period of Jupiter, the period of Mars, the period of all the different other planets, and you will. So this is our gravitational force equation. F big G, gm1m2 over r squared, times a little r hat. Notice it's a vector. We're getting a little more stringent about that. R hat is just a vector, unit vector, that's the little hat, that goes towards the center of whatever the other mass is when you're looking at the force on some mass. So like if I'm a mass, and my r hat's going to go straight towards the center of the Earth. If the Earth is the force we're trying to find on, it's going to go straight towards my center of mass. And so that's what r hat is. Notice we have a really small constant. Last year, mostly we combined these three parts of this to make that into the acceleration of a person would be 9.81. And if we had a person, an average mass for a person might be 100 kilograms. And we could find the force on the person just by going mg, we get 981. But we know that every force has an equal and opposite force. So there's a force on the planet that is the same. And so the planet Earth has a force on it that's 9.81. But since the mass of the Earth is so huge, 6 times 10 to the 24th, the acceleration of the Earth is only 1.6 times 10 to the negative 22nd. And so you can't really see that. But realize this F equals mg that we have learned is only true at sea level on the Earth. So even if we go up or down a little bit on a mountain or down underneath the ocean, G changes. And especially when we get out into orbit, G is definitely not the same, so we cannot use our mg or our energy is mgh anymore because we're at a different place. So to get towards some of the more complicated gravity problems, we have to talk a little bit about the shell theorem. Shell theorem says that if we put our mass in a shell, so it was hollow, and if this mass was the same as my original mass up here, it would act as if it was a point charge right at the center of that shell. And so there would be no difference on the force on this charge over the mass over here based on these two masses, one of which is solid and the other which is a shell around the outside. But on the inside of the shell, there would be no gravitational force whatsoever. And that's because, like, if you had a shell and you were right in the center, you could see that the gravitational force from all the different sides would cancel. If I'm not in the center, I'm closer to this mass over here, and so I'd have a greater gravitational force, but there's more mass on the other side of me, and they still are going to cancel. This is very similar to the way we did charges. On the inside of a sphere of charge, there is no electrical field, there's no gravitational field, and thus no gravitational force inside of a shell. So if we're inside some kind of a massive shell, we don't feel any gravity from that shell. There's a long proof for that, but if you're interested in that, you should look on the internet. Okay, so now these are two graphs. The gravitational force as we get farther and farther from the center, so the radius is getting bigger and bigger and bigger, that's the x-axis in both of them, of a shell and then of a solid sphere. On the shell, we have no gravitational force in the beginning because we said that inside a shell there's none. Then right at the edge, we start getting a gravitational force that goes down over r squared. That's our force of gravity equals gm1m2 over r squared law formula. Now, if we had that same mass that was solid, it changes a little bit because as I'm solid, if I'm coming out farther and farther out from a solid sphere, like let's say I'm right here, everything outside of me, this part out here, is not going to affect my gravity, but everything on the inside is. And so I'm going to get a gravity that gets bigger and bigger and bigger over time. Now the amount of mass that's inside of that can be found using our old density formulas. We know that density is mass over volume. We know that the volume of a sphere is 4/3 pi r squared, and so our mass becomes the density times 4/3 pi r, not squared, sorry, cubed. And that is what we plug in for our m prime as we are going out through the sphere. When we do that, my r cubed and my r squared cancel out to just be an r, and so our force of gravity as we come out of a solid sphere ends up being a direct relationship. So we get a nice straight line for the gravity, and then it falls off as r squared, just like this one did over here, because once we're outside of it, all the mass acts like a point mass in the center. So that's kind of weird, but it goes into some things that we need next semester. And they definitely put this graph on a lot of the tests, so make sure that you followed that or we'll talk about it. Just like we had some graphs for force, we also have some graphs, the same looking graphs for G. Because it turns out that the gravitational field, the G, that was 9.8 for so long, on the surface of the Earth is different in different places. Now the graphs look exactly the same because my G ends up being G mass of the Earth over r squared, just everything but the m, and so the m, which was a constant, changes how up and down it is, but the graphs look exactly the same. I have no gravitational field on the inside of a shell. When I get outside of it, it falls off as r squared. And the same thing happens to G as the force. It goes up linearly, and then 1 over r squared force out of it. We're a little freaked out by G changing. But G can change as long as we're on the surface of the Earth. We've done a lot of problems on the surface of the Earth, but there are other places where we need to find the gravitational field. Welcome to Physics C. Since it is Physics C, we got to do some derivatives. We want to find the potential energy formula. Remember, this is it. We had it from last year. We had that weird negative in there that we never really explained too much. And it's because of our integral that we're going to do. Integral we're going to do right now. To find the u, we want to take integral of the negative f dr. There are a lot of negatives here, so bear with me. This negative here comes from the fact that it's going towards the center of the Earth. Okay, so the force would be negative. But then there's a negative in my du, and so those two negatives cancel, and so we end up doing the positive integral of g mass of the Earth m over r squared, which we can write as mass of the Earth mass r to the -2nd. Then to get u, we want to integrate that. When we integrate that, we get r to the -1, and we have to divide by -1, and so we end up getting negative g m1 m2 over r, thus explaining that weird negative that we didn't really get. That's going to cause us some weirdness very soon. Are you ready? Not quite yet. One more last easy thing. If we are taking more than two particles and putting them close to each other, like M1, M2, M3, to find the potential energy that this system has, we have to find the potential energy between M1, M2, M2, M3, and M3 and M1, thus adding them all together. Notice it's got that negative in there. And if these three things were to go out to infinity, all that potential energy that we had, that negative potential energy, would go to zero. And so all of this energy would go towards kinetic energy, which we could do a problem with. I don't think we actually do. Maybe. With two of them, we can do it easily. With three, it's kind of harder. Before we get to the harder, it's time for our snack. I have to be honest with you. I'm a little afraid of this snack. Our snack today is a cheese with a deceptively nice name called Lorelei. That's a picture of it right there. Doesn't it look nice? When I was growing up, my dad liked stinky cheese. I was afraid of it. I'm still a little afraid of it. I went to Antonelli's cheese shop, which you should too. It's an amazing place. And asked for their stinkiest cheese, and this is what they gave me. It is quite interesting. My wife would only let me keep it in the house if I put it inside 2 Tupperware containers. That's it inside there. See there, 2? Because it is rank. Now, when I went there, I asked for the stinkiest cheese, and it was really fun because they all got excited and they got it out. And they gave it to me to taste, and I tasted it before I smelled it. And I'm telling you right now that if I had smelled it first, I might not have eaten it because it is horrid. Tastes okay. All right. I'm gonna have to smell it for you, and you're gonna be really, there goes the first lid. Oh, it's already coming. Okay, here comes the second lid. Okay, all right. Okay, here it is. See, look, this is the name. Oop, you can't see it because it's backwards. Lorelei. That's Anthony's. Oh man, it's coming through the wrap. Okay. Oh, ugh. Like, I don't know, like burnt rubber. I don't know, almost dead body, but not quite. Okay. Okay. Now, oh. All right. It's even, it's hard to even open. Okay. All right. Breathe through your mouth. Breathe through your mouth. It's not quite as bad, as durian, but we're getting close to durian levels. All right, so it's kind of smooshed. I don't know. It's not as, not quite as nice looking as, there it is, Lorelei. Okay. All right, here comes the smell. Oh. Okay. All right. Okay. Oh. I know this is probably weird. Okay. To watch, but you're gonna love this, I guess, or hate it or something. Here it is, and I'm telling you, it's really hard to put in my mouth having smelled it. But I did taste it first, and it was okay at the place. And all right, here goes. Are you ready? Okay. It's such a weird experience. The smell, even putting that piece up to my mouth, the smell is... Okay, I've got to close it up. I'm sorry. I know. The taste is pretty good, actually. If you like a nice brie, ooh, it's not bad. The weirdness is that it smells so bad and tastes okay. I mean, I wouldn't say it was great, and really, you only, I think, get it because of the thrill of putting something so stinky in your mouth and being okay with it. Man, I really almost couldn't put it in my mouth there. All right, I have to put it back up. If you notice, I'm at my house doing this. My wife's gonna come in. She's gonna freak out that I did this at home instead of at school. But here, it's all sealed back up. Proof. I put it back in. And I'll bring it to school. I don't know how many of you are gonna be brave enough to do this. I'm gonna be honest with you. You probably won't be able to, some of you, but you should, because it's an experience and it's great and you can get it. It's made in the US, Lorelei, Portland, Oregon. Antonette's Tea Shop. Go there. So I took a break, brushed my teeth, cleaned every bit of anything that touched that cheese. Cheese makers are weird. Who would do that? Who would make that cheese and then send it out in the world? Eat this. I don't know. You'll have to be the judge. But I can still smell it now. It's like really old onion and garlic with a little bit of dead something. I don't know. It's interesting. Just you wait. Anyway, back to gravity stuff. So gravity is the thing that makes planets go around in circles. So we know from a couple chapters ago, mv squared of r then is going to be given by gm1m2 over r squared. And so we can solve that for v squared. If we do, we get gm over r because one of the r's cancels. If we take that and then plug it into our kinetic energy formula, we get that the kinetic energy is 1/2 times m times gm over r. That means that it's just half of the potential energy. Because remember, potential energy is gm1m2 over r, negative, and so we have to put a negative in there. And that's a little weird, right? That means that the kinetic energy of any planet going around the sun or a satellite around the Earth is always exactly half as much as its potential energy. Weird. If we apply this to energies, we can find out what the escape velocity at the surface of the Earth is. Because we know that the energy is going to be 0 when it's escaping. Because if we have a negative potential energy when we're close to a planet, if we get it to 0, that means we're infinitely far away, we've escaped. So 1/2 mv squared minus gm1m2 over r would be 0. We can solve for the escape velocity where we get here, and then we can throw in our g because it's a number we know, and that gets rid of the g, the m, and the r, and we just end up with the escape velocity being the square root of 2g radius of the Earth. Very famous formula. That number is really important for us because that's the speed we have to get an object away from our planet, away from the gravitational well that is planet Earth. And notice that since the escape speed occurs when the kinetic energy is equal to u, and we know the kinetic energy is half as much as the potential energy at any given point, you have to give an object twice as much energy as it already has to escape the gravitational field at any one time. That stuff starts getting weird because all the g's and the m's and the r's, but as long as you carefully write all your equations, your force equations, your energy equations, it's not too bad. You just got to be careful and not to make sure you don't get freaked out. Speaking of freaked out, here is a classic physics problem that freaks some people out. It has to do with drilling a hole all the way through the planet. It's not possible, so it's kind of a thought experiment, but if we could drill a perfect hole all the way through planet Earth, that's what the little green thing is, and drop a mass into that hole, the gravity of the surface would be 9.8, but as it went in, it'd get less and less and less and less force on it, right? And so if we started with this, and we threw in our rho times 4/3 pi r squared again, we end up with this equation again. The force is 4/3 g m times rho times pi times r. And if you notice, that means that the force is all these things that are constant times the distance. And we know that if we have force equals some constant times x, that is our condition for simple harmonic motion. So what happens if you drop an object down a hole through the middle of the planet? It oscillates in simple harmonic motion, back and forth and back and forth and back and forth and back and forth. So if you stood there waiting after you dropped it, after a certain amount of time, which you could calculate, do the period, we know the formula, it would come back up and hover for a second in front of you right where you dropped it, and then it would go straight back down on the planet again and come back. That would be awesome. And while we're talking about simple harmonic motion, there's a couple more that we need to talk about now that we know angular things. It turns out that we can have something called a torsional pendulum, which instead of restoring force, we are restoring torque. And it turns out that most torsional pendulums are linear, which means that the torque is equal to some constant times theta, instead of our force being some constant times x, which means that we get simple harmonic motion again, just like we did for forces, and we get a very similar period. The only difference is, instead of the m that we had from a linear, we put I. Instead of the k that we had there, we put a capital K because it's a different constant for torsional. But the formula looks very similar for a twisty, 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 twisty. We could use that to solve for our I, and we're going to do an experiment soon to find out what that I is, of an object attached to a torsional pendulum. twist it back and forth, get the period, find I. That may have been too many simple harmonic motions, but you got one more. A physical pendulum is a pendulum where not all the masses at them end. And so your mass can be evenly distributed. So let's say you have a weird shaped thing pivoting around that point right there. So this is going to go back and forth. Any object, a ruler, for instance, would be a physical pendulum because not all the mass is at the end. And if that's the case, our torque would end up being mg sine theta, not all of gravity, but only the part of gravity putting it towards the center, times h. And so then I get mgh times theta, and I know that mgh is then going to become my k, my capital K, in my torsional pendulum equation, and I get that period is 2 pi square root of I, again we know that I need to know the I, whatever regular shape it is, over mgh. And notice it reduces to what we know for a regular pendulum. If you put I equals mh squared, one of the h's will cancel and that becomes my L, and I get the exact same equation that I had before. Physical pendulums, I over mgh instead of L over g inside my square root for my period. So I can see how things could be a little complicated for this chapter. You can see it too. Nothing in there was difficult, but it's all so much, like all the little parts. But what you need to do, you need to find it in your heart. You need to defy gravity. Defy the fact that it is hard. It is easy. Do not get confused. Do not get intimidated. Follow your equations the way you know you're supposed to. Trust physics. Trust the magic of physics. Fly and defy.